In this tutorial, we will see about relationship among elastic constants. This is part 2. Earlier, we have seen relationship among elastic constants, that is relation between y and k, relation between k and omega, etc. So, today in this relationship among elastic constants, in this video tutorial, we will consider about modulus of rigidity, that is eta, how it is related to Young's modulus, how it is related to the Poisson's ratio, etc. So let us proceed. See, this is cube of a unit length, that is a capital, suppose the L unit length. After the application of force along x direction in this manner, so forces acting parallel to x axis compresses this cube in this manner along x direction. While there are no forces acting parallel to z axis, so there is no change at all along z axis. So z axis is null and there is no role of z axis at present. While along y axis, forces acting parallel to y-axis extended this cube in this manner. So this much compression towards the origin takes place, and this much extension along y-axis takes place. So compression along x-axis and extension along y-axis, while there is no change at along z-axis takes place. So this is about the compression and extension along x and y-axis respectively we have considered in this case. So after considering application of force, initially such a type of cube was there. So after application of force, compression takes place along x-axis and extension takes place along y-axis. How change in shape and size of the cube takes place. So forces acting parallel to x-axis compresses cube, no forces acting parallel to z-axis, and forces acting parallel to y-axis extended this cube in this manner vertically in the upward direction. So from this diagram, it is clear that how extension and compression takes place uh, along both the axes x and y. So along x-axis there is a compression and along y-axis there is extension. For the sake of simplicity, sake of understanding, only we are taking one phase. So this is the one phase of the cube which we have taken into consideration. So along x-axis how compression takes place and along y-axis how extension takes place. So this is the figure for the sake of clarity, for the sake of understanding. Now already we have seen what is Young's modulus. Young's modulus is ratio of stress and strain. What is stress? Stress is force divided by area and strain is change in length per unit original length. That is, if length of the cube is unit, then capital Y, that is Young's modulus, is equal to capital F divided by L. Because if there is a unit length, one side of the cube is suppose 1, then area 1 into 1, that is 1. Change in length per unit original length. So this original length is suppose 1. That is why there is Y is equal to F divided by L. That is, then extension or elongation along y-axis is L is equal to capital F divided by Y. And compression or negative elongation along x-axis is L dash is equal to minus capital F divided by Y. We have seen about Poisson's ratio, which is denoted with the letter sigma, and it is equal to lateral strain divided by longitudinal strain, lateral strain and longitudinal strain. That is, lateral strain is equal to sigma into longitudinal strain. Now, extension Ex parallel to x-axis is given as Ex is equal to minus f divided by y minus sigma into f divided by y, and which is equal to minus f divided by y into bracket 1 plus sigma. Extension, there is a word used in this case extension, but the sign is given there minus. Negative extension is nothing but the compression. Negative extension is nothing but the compression along x-axis. Similarly, the net extension Ey parallel to y-axis and is given as Ey is equal to capital F divided by y plus sigma into capital F divided by y is equal to capital F divided by y into bracket 1 plus sigma. This is suppose second equation. Similarly, the net extension Ez parallel to z-axis is given as there is no force acting parallel to z-axis. Since there is no point about extension, and that is why Ez is equal to 0. Since there is no force, no extension, no activity along z-axis. This is equation suppose 3. It is seen from equations 1 and 2 that there is an extension along y-axis of f of y into bracket 1 plus sigma and compression along x-axis of the same magnitude. Since equal extension and compression strains are produced simultaneously at right angles to each other, they are equal to shear theta. So theta is equal to f divided by y into bracket 1 plus sigma plus capital F divided by y into 1 plus sigma is equal to 2 into capital F divided by y into bracket 1 plus sigma. This is suppose equation 4. Also, it can be shown that an extension stress F and a compression stress F at right angles to each other are equal to shearing stress F. The angle of shear is theta. So from that, modulus of rigidity, which is denoted with the letter eta, and which is equal to shear stress divided by shear strain. That is, modulus of rigidity is the ratio of shear stress and shear strain. So from this, we get F divided by 1 because unit length, that is why value of area is 1, and shear strain, that is theta. So F divided by theta, this is suppose equation 5. Theta is equal to 2 into F divided by y into bracket 1 plus sigma, and eta is equal to F divided by theta, and which is equal to capital Y divided by 2 into bracket 1 plus sigma. So from this, therefore rearranging the terms, capital Y is equal to 2 eta into bracket 1 plus sigma. In the previous video tutorial, we have seen in the previous article relationship among elastic constant that Y is equal to 3k into bracket 1 minus 2 sigma that we have seen. K was there and here eta is there. K is a bulk modulus and eta is modulus of rigidity. So how Young's modulus and Poisson's ratio and modulus of rigidity related to one another. So this is shown in this tutorial.